Responsibility for the conduct of VALA uniform was assigned by the Secretary of Defense to the Advanced Research Projects Agency in September 1959. The VALA uniform mission is that of developing an accurate system for long-range detection, location, and identification of underground nuclear explosions. The mission is divided into 6 subsidiary tasks. This interim progress report primarily concerns Task 4, which is the measurement and evaluation of the effects of underground nuclear and chemical explosions. Some of our data will also concern activities of other tasks, since they are all interrelated to at least some degree. The orderly explosion research program, in the form originally planned for Task 4, was set aside after large-scale Soviet weapon testing was abruptly restarted on 1 September 1961. 2 weeks later, the United States series of small underground explosions was started at the Nevada test site. The exact shot depths, yields, and geological media selected for these explosions were governed by the needs of the AEC's weapon development program, in which radiation safety, speed, and economy were paramount. It was seldom practical to select the shot conditions which would be most suitable for the development of scaling parameters and other studies in the VALA uniform program. As a consequence, VALA was revised and, in a sense, grafted onto the Department of Defense and Atomic Energy Commission weapons test programs. They have continued on that basis ever since, making the best of all opportunities. Up to 1 August 1962, there have been 48 subsurface detonations at the Nevada site. These shots in general, and the Plowshare Gnome shot in New Mexico in particular, have undoubtedly been the most thoroughly instrumented and recorded seismic events in history. The Task 4 aspect of VALA uniform has itself been subdivided into nearly 24 separate experiments, some administered by the Defense Atomic Support Agency and the rest by the Air Force Technical Applications Center. The principal laboratories participating in these experiments included Edgerton, Gurmahausen, and Greer, Engineer Research and Development, Texas Instruments, Sandia Corporation, Space General, Space Technology Laboratories, Stanford Research Institute, the Geotechnical Corporation, United Electrodynamics, U.S. Coast and Geodetic Survey, U.S. Geological Survey, and Waterways Experiment Station. Most of the Defense Atomic Support Agency experiments were concerned with basic research in regions close to the point of detonation. On several shots, detailed studies were made of free field particle motion at depth in the parameters of acceleration, velocity, and displacement. This was done along several radii extending from the immediate vicinity of the explosion into the region of elastic behavior. Surface and near-surface measurements were also made of these close-in Earth motions to determine the strong transient response at a number of ranges, extending out to where more sensitive, strong motion seismographs could operate. Vertical ground motion near surface zero was studied in another program. High-speed motion picture cameras with long focus telephoto lenses were trained across surface zero to detect the relative motions of fixed targets aligned in rows across that area. Another approach used cameras to observe the movement of a surface zero target in relation to a spring-suspended inertial weight. On almost all events, the U.S. Coast and Geodetic Survey made strong motion seismic measurements. One data line used an array of 11 strong motion seismographs, spaced at distances of 2,000 to 48,000 feet from surface zero. The instruments were standard coast survey types, recording acceleration and displacement on photosensitive paper. They were remotely started and pulsed with signals correlated with world time, plus or minus 25 milliseconds. For more distant seismic measurements, 6 Coast Survey recording stations in mobile trailers were spaced approximately 25 kilometers apart in a line out from surface zero. Each station recorded the 3 components of Earth motion with variable reluctance seismometers of 1 second period, and a variety of geophones spaced 1,000 feet apart on a radial line from zero. The line orientation was to the southeast for a number of shots and was swung around to the west for others to obtain a longer profile. A number of pre-shot and post-shot records were also made to establish background noise levels and to learn whether any distinctive pattern of aftershock behavior could be expected. On a number of representative shots, extensive shock spectrum measurements were made at a series of discrete frequencies between 1 and 300 cycles per second. The instruments were reed gauges, masses mounted on the ends of cantilever springs or reeds with the desired natural frequencies. One group of experiments concerned the electromagnetic waves and magnetic fields generated by underground nuclear explosions. They utilized such antenna structures as earth probes, flat and vertical loops, multi-turn loops, and long wire. Frequencies from DC to 10 kilocycles were covered, some of them at ranges out to 50 miles. These researches, while basic in nature, were primarily designed to determine whether any of the electromagnetic phenomena had direct utility for the Vela Uniform mission, long-range detection and identification of underground nuclear events. In early returns from these programs, no significant signal has been detected beyond approximately 20 miles. Another group of programs was aimed at developing and testing the necessary on-site inspection techniques required to determine from surface indications whether a suspicious seismic event was merely an earthquake or actually nuclear in origin. These studies were carried out on the first shot, Antler, and on several other shots of the series. One program was based on the observation that many trees in surface zero areas suffered root damage from underground nuclear events in Nevada in previous years. Such root damage will, within a few days or weeks, change the reflectance characteristics of affected vegetation. In the current series, a portable reflectance spectrophotometer, the only one in the United States, was used to measure pre-shot and post-shot reflectance on selected events. The objective was to determine optimum film and filter combinations, which would provide the greatest tone contrast for aerial survey work in any international inspection effort. Further inspection programs, both visual and photographic, were directed toward location of rock slides, ground fissures, radioactive contamination, dust deposits, displaced stones and humus, dirt disposal sites, and other activities which would tend to locate an underground explosion. There were some shots in alluvium in which no such detailed and minute checking would have been required. On these, there was an aftershock collapse of surface material into the explosion-created cavity, leaving a large and conspicuous crater. Other complex but small-scale on-site detection studies have been made on such possible indicators as shock-induced changes in soil density, soil electric resistivity, and thermoluminescence in surface rocks. In addition, gamma-ray spectrometer surveys have found characteristic vented or microvented fission product photopeaks without resorting to core drilling over completely buried explosions. It has been estimated that these various surface techniques have a capability of locating the epicenter of an underground nuclear shot to within less than 100 feet, if other data can first direct the search to within a mile of the surface zero. Prolonged post-shot seismic monitoring was carried out on 4 shots, selected to give a representative spectrum of aftershock performance in the 4 media in which shots were fired during the series: alluvium, volcanic tuff, bedded salt, and granite. These events were all in low seismic areas at depths between 580 and 1,350 feet. The objective was to extend our knowledge of the value of aftershock monitoring as an on-site inspection technique. The same mobile trailer recording units which monitored the nuclear events also recorded since June 1962 the aftershocks from 10 earthquakes in California and Nevada, to be used for comparison with the explosions which were in the same magnitude scale. The preliminary conclusion from available data is that most earthquakes and underground explosions differ in their aftershock characteristics. The explosion aftershocks are centralized and do not usually continue to occur for periods exceeding 3 days, whereas earthquake aftershocks usually are geographically scattered and may continue for weeks. The largest and most complex single Task 4 operation was that of the Long-Range Seismic Measurement Program. With only a limited capability at the abrupt start of the test series, an orderly buildup was initiated, and the planned level of 40 seismic field teams was reached in mid-November 1961. Each team operated in its own mobile recording van, equipped with 3 component systems of both short and long period seismographs. The short period systems used Benioff variable reluctance seismometers with 1 second natural periods. The long period systems use spring nether seismometers with a natural period of about 20 seconds. Radio timing signals from station WWV were recorded to give correlation with world time within 1/10 second. The long-range program operated with success on every shot of the series, with mobile station locations between 75 and 4,000 kilometers from the test site. In addition to the total of 46 Vela uniform mobile seismic stations which recorded the Nevada explosions, further intermediate range measurements were made by up to 5 mobile seismic units from the University of Michigan. A large number of recordings were also made by observatories and university stations. The Atomic Energy Commission's Nome shot was fired approximately 1,200 feet below the surface in bedded salt near Carlsbad, New Mexico. It was the first U.S. continental underground shot outside of Nevada, and the best recorded U.S. shot to date. In addition to permanent stations around the country, more than 90 mobile stations worked on Nome, including some 39 volunteer units from the exploration geophysics industry. Worldwide, Nome was also detected by 3 stations in Canada, and weekly by 2 in Finland and 2 in Sweden. The word detected is used with the usual connotation here. That is, while the distant stations were able to locate at least single phase arrivals from Nome, largely because of prior information on the shot timing, none of them suggested that their records would identify the event as an explosion. Beyond the first few hundred kilometers from Nome, P-sub-N arrival times to the east were much earlier than at the same distances in the west. These travel time anomalies are the greatest ever observed in the U.S. The disagreements total as much as 12 seconds at 1,700 kilometers. Similar behavior of both body waves and surface waves suggests that crustal anomalies are not a sufficient explanation of these large discrepancies. Beyond 1,000 kilometers, when P sub n amplitudes first became clearly measurable, it developed that the maximum P sub n amplitudes also ran much higher to the east than to the west. Perhaps the greatest variation occurred at 1,500 kilometers. P sub n motion at Jackson, Tennessee was 150 times greater than at Mina, Nevada. Plotting of residuals from Nome and other profile work also indicate that a substantial anomaly is centered approximately on the Nevada test site. This will merit consideration in any seismic calculations based on explosions at that location. Along the profile between Carlsbad and the Nevada site, it was found that body waves had 2.5 to 3 times greater amplitude than would have been expected from a shot of equal yield in the Nevada tuff. This may be a reasonably accurate ratio for the energy coupling efficiencies of explosions in salt as against those in volcanic tuff. Further data on energy coupling and transmission were derived from the Hard Hat event, fired some 950 feet deep in competent granite at the Nevada site. Comparisons of signal strength of body waves indicated that it has approximately the same effective energy coupling as tuff. It is interesting to note that Hard Hat in granite produced strong surface waves, while those from Nome in salt were very weak. An important finding of the Nevada series was that shots fired in dry alluvium generated signals less than 1/5 to 1/10 the size of those from an equal yield in tuff. Thus, dry alluvium would obviously be the medium of choice for anyone attempting to fire an unmuffled underground nuclear explosion without detection. The 5-kiloton Hard Hat shot in granite produced a signal meeting defined criteria for first motion detection out to 745 kilometers. By contrast, the Fisher shot, 13.5 kilotons fired in alluvium, met first motion requirements only to 410 kilometers. A majority of the stations within 1,000 kilometers of these shots detected the several surface phases required for throw-away depth of focus determinations. However, the crustal velocity variations were far too great for any useful accuracy. The calculated depths included figures like 50 to 65 kilometers well into earthquake depths. For another check, this time on accuracy of epicenter determination, data was utilized from a random group of stations with representative Geneva-type spacing around the Nevada site. Hard Hat and Fisher were computed to be some 7 kilometers to 10 kilometers, respectively, distant from their actual detonation points, which would generate respective search areas of 150 and 300 square kilometers. A still wider error appeared in a calculation for the epicenter of the Nome event, based on observed travel times and standard velocity tables. This put the epicenter about 30 kilometers east of the actual site, generating a potential search area of some 2,700 square kilometers. However, the error in Nome location can be reduced from 30 kilometers to less than 5 kilometers if we use a newly constructed United States travel time map, which incorporates findings from the current explosion series. Another interesting experiment was the recording of 5 nougat explosions at water depths of about 4,000 feet off Santa Catalina Island, some 300 miles from the Nevada test site. Preliminary contractor evaluations comparing the ocean bottom records and university station records indicate that the ocean bottom data compare favorably with those obtained at the better land stations with respect to definition of first arrival time and phase distinction. The Nougat test series has also been used in the early field evaluation of new types of seismic detectors. Thus, on the Hard Hat shot, the first useful record obtained with a downhole seismic detector at large depths were obtained from the 7,500 foot level in an abandoned oil well near Hobart, Oklahoma. Similar encouraging results have been obtained from the 10,000-foot level of a hole near Dallas, Texas. The record from this hole for the haymaker shot shows an improvement in signal-to-noise ratio of about 5.5 times between the surface and downhole detectors at a distance of 1,100 miles from the Nevada test site. As a consequence of the large number of underground nuclear explosions in the Nougat series and the devoted efforts of hundreds of technicians and scientists, an important body of knowledge has now been accumulated. This information is now undergoing extensive evaluation to determine its implications in the design of a practical underground nuclear test ban control system. In the meantime, it is anticipated that such projected nuclear explosions as Shoal, Coach, the Storax series, and the Dribble series will provide further unique data of the same general type to forward the objectives of the Vela Uniform program.